Okay, yeah, you got it on there. Cool.
Yeah, and now what I'm going to do is I'm going to...
Cool, so it came up on here.
Can it still see? It's not showing the video.
Is this supposed to be screen sharing right now?
Oh, maybe it is.
Yeah, it is. It's showing your screen. Oh, that's why you couldn't start the recording, because you're in the screen share. That's why it wouldn't full screen.
All right, I hope people can hear me okay. Welcome to another exciting microprocessor lab. What I've got here today is, first of all, I've created a new assignment that you can upload your lab to using Microsoft Word. So if what you want to do is show me your Tinkercad simulation and your code, paste it into a Word document, and then submit it as homework 1. I've also created a homework number 2. And homework number 2 is another Tinkercad variant, but this one just a little bit different. And what we're going to do here is I'm going to show you the microprocessor lab. And here is the Vimeo. Let's see if we can have that play. So now, I don't want to join Vimeo. I just want to play a video. Let's close this and play. And you can't hear it. I don't know why we can't hear it. It's a mystery. It really is. I mean, but what I hate this nonsense. There's no way to play a video and hear it at the same time. This is stupid. Anyway, what I've got here is a 3-pin system, which is capable of sensing distance. It sends out a chirp, and then it proceeds to listen for the chirp return. The chirp return comes back as a measure in microseconds, and what you want to do is you want to take that microsecond number and multiply it by a constant, which will give you a number in centimeters. When you click on the little green area in between the two sensors, right over here, you get a chance to be able to adjust the simulated target. The simulated target is something you drag around with the mouse. It doesn't work at all with a mobile device for whatever reason. And then it'll print out inches and centimeters as long as it's inside of this cone. Otherwise, it has a near-field blindness, just like the blindness you get with a stereo sensor. You have your finger right in between your nose, right on the bridge of your nose and between your eyes. You can't really see what's going on. So, as a result, this has near-field blindness, which is similar to any stereoscopic system. What I've done over here is I set up pin 7 as my input. You can see what is green is being wired to pin 7. That's your signal. And I got a serial begin over here so I can get print statements out. And I got a read of the ultrasonic sensor, which is reading in from pin 7. And so what you've got to do is when you read the ultrasonic distance, you put in 7 over here because it shows you can have multiple sensors. And then as it comes in microseconds, you want to convert it to centimeters, so you multiply it by this constant. And then if you want to go from centimeters to inches, it's 2.54 centimeters to the inch, so you divide by 2.54, and then you get inches and centimeters, and that's what gets printed out over here, inches and centimeters. Then you wait for 100 milliseconds, and you go back and repeat. And so the only, sort of tricky bit is to read ultrasonic distance, and what you're doing over here is you set pin 7, that's over here as your output. You delay in microseconds 2, then you do your assert from 1 to pin 7, that puts out a chirp, wait 10 microseconds, then assert pin 7 as a 0, and then you do the input from that pin, and it will read in your time delay in microseconds. So what you're looking for is a mechanism for maximizing the probability of a return from a chirp that's being emitted. Usually these chirps are done in multiple frequencies, and they do that in order to maximize the probability of the bounce back. The Polaroid sensor, for example, has a chirp that's done in 4 different frequencies because different targets reflect differently. So a chirp isn't just one frequency, it's a few different frequencies, but you can control that in principle. But we're not going to get into that fine-grained control. We're going to accept the results now. This particular sensor has 3 pins. Chris, would you do me a favor and poke around in the drawer and see if you can find a sensor with 4 pins? Yeah. And what I'll do over in here is I'll show you how you can do a slightly different approach. We'll do a 4-pin sensor because I think what you have here in the lab is a 4-pin sensor.
You can use the 4 pins as a 3-pin sensor, but it's a little more complicated and not really necessary.
Yeah, I know you can. I think we're just going to do it with the 4-pin sensor in general. So let's just see what it's like to do it with a 4-pin sensor. And this time, we're going to do it just like last time, only with a difference. And the difference is, what we're going to do, let's make this full screen, is we're going to have pins 7 and 6. Okay. Grace, did you find any sonar sensors for the students? And then as you get closer, what we'll do is we'll increase the number of LEDs that are lit. So we're going to combine the blinky light lab 1 with the ultrasonic sensor. And then what you're going to do over in here is you're going to see is power, VCC, which is the red one in here, and the ground, GND, which goes to the ground pin over here, and made that a black wire. And I'm going to try and stick to that convention, okay? VCC will be red, ground will be black. And these videos are going to be part of homework number 2, which is due at the end of next week's Wednesday day, right? So 1 week from now, end of day, Wednesday, homework 2 will be due. And what I did over here was, now with this 4-pin version of the HC-SR04, you click on the crystal, you can drag this around, you can see he's reading out the actual distance. But what you really want to do is you want to see how the LEDs work. I don't know if you can see the LEDs, but they're lighting up. As you get closer, they light up more, and you get farther away, fewer of them will lit up. It doesn't show as nicely on the screen as it does on the computer monitor. You got enough sensors there?
Yeah. Yeah, we won't have enough for the next group 2, so I'm going to need them back.
Yeah, we'll have to return. That's it. But if you can get it working here, you don't actually have to do the simulation right up. I would accept an implementation that's here in the lab. So if you can quickly cobble this together, as I've shown you here, pins 7 and 6 going into, you can see that over here, your trigger and echo pins, respectively. I think you should be all fine. Here is a little subroutine for reading any trigger pin, any echo pin, so you can set it up yourself. And then what we'll do is we'll write the trigger pin low, delay for 2 milliseconds, then write it high. That will emit a chirp. Wait for 10 microseconds, and time to see how long it takes the echo to come back on input. And then we'll return the time in microseconds from pulse in, and then multiply by that same constant we saw from before. So now, your travel time in microseconds times this number gives you centimeters. So I'll just keep reading the centimeters in here, and print the centimeters out, just like before. But now it's different. Now it's different. If you go over 250 centimeters, if it's between 250 and 175 centimeters, the first thing will, it's more than an inch, so you put up the first LED. If you go between 175 and 100, you change the pattern. If you go less than 100, you change the pattern again. As you get closer, the number of LEDs increases. So that's my shtick, but it's not a clean implementation. So I thought what I would do is I would say, why don't we parameterize these three lines, which are practically duplicated. And what we'll do is we'll create a new procedure. And this procedure will give us numbers for the digital lights that are something like 111 or 000, depending on everything on or everything off. And we'll call that right LEDs. And I thought maybe I should do something like LED A, LED B, and LED C with 3 different LEDs. And that was just sort of my thing. I could have called it anything I wanted, but this is just parameterized so I can address the different LEDs. And I know they're on pins 13, 11, and 9. And when I wired things up, I made sure that the one on pin 13 had its ground going right into the GND. But the others are all going to have even numbers, so the 12 and 10 for their grounds. And then we'll just have to insert 13, 11, and 9 to turn on LEDs A, B, and C. And so what I thought I would do is do something like this. When you do a right LEDs, it'll just be 000 when you want low or low. It'll be 100 when you want high, low, low. And then you don't have to have these 3 lines every time. It shortens the program and makes life a little bit simpler. So that would be like 110. And you'll see me doing that over here. And then this should be 111. Right, so that kind of simplifies the code just a little bit, because otherwise you're kind of duplicating the code all over the place. It kind of doesn't make sense. You don't want to do that. Duplicate code is like a bad smell in the program, So you get rid of that. And then and that's what they call it. That's called a bad smell. So refactoring, that's what I just did. Refactored the code to make it work just the same as before. With just the same as before, but with a difference, and the difference is the code looks a little bit cleaner, a little bit more elegant. And so that's the shtick that I got. And you can probably run this in simulation, or if you like, what you can do is you can implement these things directly. Let's see if I can find. I want to go back. I want to find that code right here. So there's the code. I'm not going to hit play yet. Instead, what I'm going to do is I'll just leave that up there in case you want to see it. In fact, maybe what I can do, I can increase the size. No, you cannot increase the size. I guess that's as big as it gets, unfortunately. Now, the other way you can go with this type of code is if you've got the Arduino IDE, you can find examples, right? So if you wanted to go and do it with examples, keeping in mind pins 7 and 6 are your trigger and echo respectively, you would run the Arduino IDE. What I'm going to try and do in here is I'm going to try and increase the font size a little bit. I think you can do that here using Control Plus. So what I'll do is I'll just Control Plus a few times so you can see things. We'll format for television. Formatting for broadcast. Can people see that okay in the back? No? Make it a little bigger? Can you see it okay in the back now? What we'll do is we'll look for some samples. So let's see if we can find examples involving sensors. And I don't see one. Oh, yeah, here's one ping. And that reads from the ultrasonic rangefinder. But this is a 3-pin version, not, I think it's a 3-pin version. Yeah, and not the 4-pin version. So you want a slightly different version of your pin. Let's see what other examples we've got. So you're looking for an HC, I think it's called the SR04.
Yeah.
So it should be one of these in here. And if we can't find it, we may have to cut and paste it to, isn't that funny? I thought we had one in here. I have one at home, but I don't have one on this system.
Did you want to do it without a library first?
No, I just wanted to grab the example off of the Tinkercad, but I can't seem to log into my Tinkercad.
Because when you have the what is it, ping library downloaded, there's examples that use that library, but I don't know if you wanted to use the library.
I don't see any library being downloaded here. Do you?
That would, no, it's not, but there is a simpler, there's a fairly simple,
see, that's a 3-pin. That's a 3-pin.
Yes. When you can do those as a 3-pin, but we don't want to.
Yeah, I don't want to.
No,
I want to get a 4-pin example.
Totally.
So let's get a 4-pin ultrasonic sensor Arduino code. There it is.
Yeah.
We'll just grab one off the net. That's fine. And let's see if we can grab this one. This one's looking okay.
Oh, no, that's testing. That was an ad.
Oh.
Next one.
There we go. Let's see if we'll give you the code without a hassle. Somewhere in here, he should give you the code.
It's a pretty good explanation.
A very nice explanation. What does it say here?
Examples.
I can't zoom in. I can't read it.
Oh, he's just selecting the Arduino code next.
So here's the code.
Yeah. He's using, oh no, he's not using library. Cool.
Select all, paste, and now what do we got? All right. Did you find enough ultrasonic sensors so I could have one?
Yeah.
So this would go to 7, and that would go to 6. And that one here? Oh, great. And I think people are going to need DuPont cables.
Yeah.
I know I do. DuPont cables. So DuPont cables these are the cables that allow you to plug the wires coming out of the sensor into the input of the Arduino, and you're going to need 4 cables. It'll be a female to male conversion for the cables for each one of the sensors. So for everyone in class, you'll need 4 cables, and you might like to find red and black for the, the power and ground. And so if you wanted to, you can do what I just did, which is to hook up pins 6 and 7 as your echo and trigger, respectively. And now you can see how the HC SR04 is being run. That's the kind that we have here in the shop. And you can see how the trigger is being held to low for 2 seconds, then gone to high for 10 microseconds. And then we're using a slightly different distance in here. This is divided by 2 for some reason, so it's 0.034 divided by 2, which is the same number as we had before. Speed of sound, but in round trip, going and back. And then it'll print it out. So that'll give you a very basic opportunity to get things to work. Here's the sensor. I'm holding it up for you guys to see. It's got the 4 pins on it. If you're at home watching this and you don't have the hardware, you might as well use Tinkercad because we don't have enough of these to go around for everybody. And I think we're struggling with the DuPont cables right now. Let's see how many participants we have here. It's only me. So what we'll do is we'll stop the video for now. Let's stop the recording.
Also, we're extremely low on female male DuPonts.